Dear students, welcome to EPG Pathshala. Today the module is titled F distribution and tests of significance based upon the F distribution. In our earlier modules we have seen how to use the T distribution for performing comparing the groups between two groups, or the means of the two groups. We can compare using the T distribution by the T tests. And also the T distribution is also used for calculating the confidence interval of the mean and other statistical assumptions. So the F distribution is quite similar, and the name F came from the Fisher, or one of the founding father of the statistics as well as for the population genetics. So the F distribution is very important. We have seen the one use of the F distribution in our T distribution module, that F distribution is used to calculate the equality of variance between the two group means. So that is one assumption. Assumption is called homoscedasticity. Before doing the T distribution, the T test, the group variance have to be similar. So that assumption, to test it, we can use the F test. Yet another important test for the F distribution is the ANOVA. So there are two types of ANOVA, the matched ANOVA or unmatched ANOVA, or one factor ANOVA and two factor ANOVA, or one way ANOVA and two way ANOVA. There are multiple types of ANOVA. Some of the ANOVA tests that I will be describing in this particular module. So now coming to that, F distribution, or also called Fisher distribution, is a type of a continuous probability distribution with exact probabilities of every F scores are known. This enables us to calculate the p-value from a given F ratio. F ratios from null hypothesis is plotted as in a probability histogram is called F distribution. The shape of F distribution depends only on the degree of freedom df of the numerator and the denominator. When both of the degree of freedom is small, the shape is distinctly skewed to the right. With a high degree of freedom, distribution becomes bell-shaped, although it would still become skewed to the right. As you can see in this particular diagram, as the degree of freedom is low, that is actually there are two degree of freedom in F distribution of numerator and denominator, or F d1 and d2. So d1 is numerator, d2 is denominator. So both the degree of freedom is low. As you can see in the red one, it is L shaped, so it is skewed to the right. So skewed to the right because the tail is towards the right. So as the degree of freedom increases, it becomes more and more bell shaped. As you can see, the light blue in this graph is the one with a very high degree of freedom or a very high sample size. So at each combination of these two degree of freedom, F distribution can be calculated using intricacies of the calculus, especially the area below the F distribution. To calculate that, you have to use the calculus. At each of these distributions, at each combinations of degree of freedom numerator and denominator, we can calculate the area under the significance level or the critical or threshold p-value alpha at these tails. These values can be presented in a tabular format, the so-called F distribution tables, where one can look up a value called F critical. One can compare this F critical value found from the table and the F ratio calculated from the data to make inferences about the statistical significance. If F critical at significance level of 0.05 is less than the F ratio, we can infer that the p-value must be less than 0.05, and we can reject the null hypothesis. So F distribution is used to test whether the two groups have the equal variances, one of the assumptions of the unpaired T test, as we have seen that in the module 18. The most important use of F distribution is the F test, also known as ANOVA, analysis of variance, for comparing the means of three or more groups, as discussed in this module. Keeping in mind that ANOVA merely compares the group means and informs us whether all groups have identical means or not. Means would not be identical if mean of one group is different from the rest. To know which group means are significantly different, we have to do multiple comparison post test, as explained later in the module. So the post test include Tukey's HSD, that is honestly signified differences, or Bonferroni adjustment of multiple T tests. So you can do this comparison of more than two groups. So the first question is that, is it independent or the dependent? So in the case it is independent. Now the question is it actually normally distributed, the Gaussian distribution, or not normally distributed? If it's normally distributed, we have to use one of these parametric tests like ANOVA. Now the question is that, is it one factor or more than one factor, two or more factors? So if it's only one factor, we have to use one way ANOVA, that is analysis of the variance, or more than one factor, we have to use two-way analysis of variance. So if it's not normally distributed for the independent group, we have to use Kruskal-Wallis one-way ANOVA by rank, which is a non-parametric test. If it is dependent and normally distributed, we have to use repeated measure ANOVA, and if it's dependent and not normally distributed, we have to use Friedman two-way ANOVA by the rank. So none of these non-parametric method like Friedman test or the Kruskal-Wallis test is not supported in Excel. So we have to use another software package like in the GraphPad Prism. So there are multiple problems with multiple comparisons, the multiple t-test for determining the significance if it's the groups are more than 2. So multiple comparisons increase the chance of finding a false positive drastically, chance of type 1 error. So the multiple t-test for comparing means of more than 2 groups should be avoided. So which ANOVA should I use? Is it one way or two way? Depends upon how many factors are there, right? So for one way ANOVA for comparing one factor means of more than 2 groups. For example, average height of the neem trees at 3 villages, average groundwater arsenic levels at 4 districts in the Gujarat. So here the response variable is only one, that is average height, right? But there are factors, the other variable, right? There is actually a treatment variable, right? Here the treatment variable is 2 in both the cases. Now in the case of two-way ANOVA for 2 factor means of more than 2 groups, again here the response variable is only one, the average height of the neem tree, but there are more than one treatment variable. Here the treatment variables are using 4 different fertilizers at 3 villages. So here the 2 factors are for fertilizers and 3 villages. So village and fertilizers are factors affecting the height, that is our response variable. So in the next example is average arsenic levels at shallow, moderate, deep wells in 4 districts. So arsenic level is our response variable, while treatment variables are 2, either the well, the wells, the types of well and the space, that is basically 4 districts. A factor is an independent treatment variable whose settings or values are controlled and varied by the experimenter. The intensity setting of the factor is called the level. Levels may be quantitative numbers or in many cases simply present or not present, or 0 or 1. Effect of temperatures on resistors. This is yet another example. Measure the resistance before and after placing it in 3 ovens set at different temperatures. Here the temperature is a factor, different temperature setting are levels. So there are 3 levels for this particular factor. So there is only one factor, which is temperature, so it's one-way ANOVA. Effect of temperature and heating time on resistors. So as you can see, there are 2 factors, so it has to be two-way ANOVA. Hypotheses that can be tested using ANOVA are, for example, if it's in the one-way ANOVA, there are only 2 hypotheses. The null hypothesis is that the mean of the factors are equal, while alternate hypothesis that the means of that particular factor are not equal. For the two-way ANOVA, there are 3 possible null hypotheses. First possibility is that there is no difference in the means of factor A. Second possibility is that there is no difference in the means of factor B, because there are 2 factors involved. So each factor we have to do that's corresponding null hypothesis. And the third possibility is that there is no interaction between the factors A and B, because there are 2 variables involved. Is there any interaction? That is also being revealed by the ANOVA. So like a correlation of the 2 variables. So possible alternate hypotheses are, for the cases 1 and 2, the means are not equal. Case 3 is that there is an interaction between A and B. So ANOVA is also making various assumptions. So assumptions include exactly same as in t-test: random sample, independent measurements, accurate data. Data is sampled from populations that are approximately Gaussian, and homoscedasticity, that equality of the variance. So the variance or the standard deviations of populations from which the samples came from are identical. We will see one example here: the increase in mouse colorectal tumor by 4 different heavy metals after feeding for a period of time. So you can see here there are 4 columns: uranium, lead, arsenic and mercury. In each column have got values. These are replicate measurements, and all the 3 has got 4 replicates, while in the case of arsenic there are only 3 elements. So factor is only one increase that can be a tumor weight. So as you can see in this particular table, it has been summarized, including each group, mean, standard deviation and variance. You can see below that particular the group respective group, and we have also seen on the right side, you can see that the rightmost column is the overall mean, that is overall mean is 77.79. From this value, the first step for the ANOVA is we have to calculate SS total. So SS is nothing but sum of squares of the difference between each of these values, 15 values, with the overall mean. So each value subtracted from the overall mean. So overall mean, so each value minus overall mean. So we have to take a summation of this. So SS total, or sum of the squares of difference. So this particular SS total is also used for calculation of standard deviation. In the module on standard deviation, you might have seen how the standard deviation is calculated by hand. So each of the value we are subtracting from, subtracted with the mean, the overall mean, and we are squaring it. So that exactly is the same thing here also we are doing SS total. And as you can see, it's much easier if you do that tabularly. The first column is the empirical observations, and the second is that each of these element subtracted with the overall mean, and the third one is you are squaring, and finally you are calculating the sum of all these values. Next is SS between. So sum of squares between group means. We have 4 groups, so we have 4 group means. To compute SS between, we have to subtract each group mean with overall mean. So it's the same thing, the overall mean is used for both, the earlier one, that is SS total, as well as for the SS between. We have to subtract each group mean with overall mean, then square this number, and finally we have to multiply with the size of each one. So this is to normalize it. To weight by the sample size, we have to multiply with the sample size. As you can see here in this particular table, each of the group mean, for example, the group mean of the uranium is 61.03, you are subtracting with the total mean, and you're going to get it is a negative 16.76. So we have to now square it to convert the negative value to the positive value. Exactly, we have explained this in the standard deviation module. So after squaring, you're multiplying with the group size. So most of the group size is 4, except in the case of arsenic, which is 3. And finally you are calculating the sum of all these values. So that is called SS between. So now the third crucial value of the ANOVA is SS within, that is sum of squares within the group means. So as you can see, SS total is equal to SS between plus SS within. So therefore SS within is equal to SS total minus SS between. So given SS total and SS between, you can calculate SS within by plugging into this formula. So that is 1923.4341 minus 1761.128. So our SS within is 162.282. So this SS within is also known as residual sum of squares or error of sum of squares. Next step is to calculate the degree of freedom for each of these sum of squares. For SS between, we have 4 groups, so that is also called K, that is total number of groups. As degree of freedom is n minus 1, degree of freedom here is 4 minus 1, that is 3. We have 4 groups, minus 1 is 3, that is our SS between degree of freedom. Degree of freedom for SS within is the overall sample size minus the number of groups, so n minus k. Here the overall sample size is 15 and number of group is 4, therefore 15 minus 4, 11 is the degree of freedom for SS within. Finally, degree of freedom for SS total is the total sample size minus 1, that is n minus 1, 15 minus 1, 14. Also degree of freedom between group plus degree of freedom within group, that is actually as you can see 3 plus 11 is also 15. So the two way to calculate the same the statistic, the degree of freedom. Now next step is to calculate the mean square. So each SS we have to divide with the respective degree of freedom. So sum of square between divided by degree of freedom between will be mean square between. So sum of square within divided by the degree of freedom of within is equal to mean square within. Now the ratio of this mean square, that is mean square between divided by mean square within, is called F ratio. So this is the final F ratio is the ANOVA test statistic. So this is all summarized in this particular table, ANOVA summary table. As you can see here, the first column is the sum of squares of between the groups, within the group, and then the total. Now the next column is degree of freedom for between the groups, within the groups, and the total. Then mean square, and finally F ratio. As you can see here, F ratio is 39.79. that is what we are using it. Also remember that the MS within, the mean square within, is a very important test statistic used in Tukey's HSD, explained later. The obtained F ratio is 39.79. So as in the case of other tests of significance, we have to find F critical from the F distribution table and then compare that F critical value with the obtained F ratio to see which is higher, right? So to calculate the F critical from the F distribution table, we have to look up the F distribution table for the alpha 0.05. In the case of F distribution table, there are multiple tables for each of this alpha. So we have to check up a specific table for the alpha 0.05, in which we have to now look at with the degree of freedom 3 and 11. So df1 is 3, df2 is 11. So in the case of F distribution table, there are 2 degree of freedom, as I told you earlier. So the value, as you can see here in this table, is at 3.59, which is far less than the calculated value 39.79. So p value must be far less than 0.05, and the difference is statistically significant. If we had looked up for other F tables with alpha 0.01 or 0.001, that is much lesser significant. To the why you want to look up that way, to avoid the the false positives, right, as I already explained in the statistical test module. So if you would have looked up in those tables as well, the critical values would be still less than the calculated value. So p value must be very less. So p value must be less than 0.001. The exact p value calculated by the Excel is 3.36 e minus 0.6. So you have to read this e as 10 power minus that value. So that is exponent, right? So 3.36 multiplied by 10 power minus 6. So that is 0.0000336. So it's very low value. So the significance must be high, extremely significant. We can also use an online calculator like the one given at the StatTrak site as given in this, but the URL is given in the slide. Keep in mind that the calculator returns a cumulative probability. We have to subtract this value from 1 to get the empirical probability. So you can do Excel for the one-way ANOVA. You have to enable the data analysis toolpack, and after enabling the data analysis toolpack, so you have to click on the ANOVA single factor. So the p value obtained is of course less than 0.001. So the differences are significant for this particular data set. Remember that a low p value indicates that the group means are significantly different. It could be because one of the 4 means is different from the rest 3, or 2 of the group means are different from the rest 2. It could also be due to the fact that all 4 means are different from each other. None of these finer details are revealed by one-way ANOVA p value. To find that out, you have to perform an appropriate multiple comparison post test, also known as post hoc test, like Tukey's HSD or Bonferroni adjustment. Here it is second example, differences in concrete setting time with varying volumes of water and cement. So these rows are water cups while columns are cement cups. As you can see, there are 2 replicate measurements. So there are 2 factors here, the cement and water, of course. So we have to go for two-way ANOVA, while the response variable is only one, the time, the setting time, cement setting time. But there are 2 factors, so two-way ANOVA. So you have to click on the data analysis in Excel, ANOVA 2-factor with replication. So the obtained p value is less than 0.001 for the factor water. So the differences are significant for water. Now for the factor cement, p is higher than 0.001. So the significance differences are not significant. NS. Now p is also high, that is higher than 0.001 for the interaction. So the significant there is no significant interaction between these 2 factors too. So only one significant finding is the water. The volume of water influences the cement setting time, rather than there is no interaction, or the cement is also not an important factor. There are other types of ANOVA The one example is repeated measures ANOVA. As a paired t-test is used to compare two groups with paired, matched or dependent measurements, we use repeated measures ANOVA for matched measurement for more than two groups. These are called matched sets or matched blocks. So whenever a value in any particular group is expected to be closer to a specific value in another group than to a random value from other groups, so that if these are actually paired, the matched, because of the way we designed that experiment, we should use the repeated measures ANOVA. To find these out, which groups are significantly different, we have to perform an appropriate multiple comparison post-test like Tukey's HSD, similar to the normal one-way ANOVA. Next variety of ANOVA is MANOVA, M-A-N-O-V-A, that is multivariate ANOVA. So MANOVA is used for comparing the effect of single categorical variable, that is exposure to tobacco for example, on the average of two or more continuous variables, for example heart rate and blood pressure. Another type of ANOVA is random effects ANOVA. Normal ANOVA is technically called fixed effects or type 1 ANOVA. In this case, the test assumes assess the means of our selected groups only without making any further extrapolations. In the case of random effects ANOVA, also called type 2 ANOVA, the test assumes that the groups that we selected are randomly selected representatives, our sample groups, of an infinite number of groups, our unknown population. And the test compares our sample group means to infer whether our infinite population group means are significantly different or not. So that is what you call the random effects ANOVA. In this, the group are assumed to be coming from a larger population of many such groups. So our test groups, the sample groups, are representatives of a larger population of many such groups. So in that case, we have to use random effects ANOVA. Finally, analysis of multimolecular variance or AMOVA is also used. So this method is to deter the population differentiation, a large contiguous population fragmenting to small isolated populations. Using molecular markers, for example RAPD or RFLP, we can use AMOVA. While AMOVA had been developed in lines of ANOVA, the two methods are quite different. So in summary, F distribution is a very important probability distribution. That is actually the null hypothesis of the F ratios are plotted as in a probability distribution. That is what you call the F distribution. So F distribution is used for the F test. So F test is a very important probability test for calculation of ANOVA and many other tests of significance. Thank you.